Hello and welcome back. In the last video, we talked about conservation of momentum when we have systems that are isolated in that they do not have any net external forces acting on the system. And I think at the end of the video, I promised to do some problems in the next video. But I think first of all, we want to do one more video on talking about what we've already been talking about and maybe a few more principles, and then we'll start working some problems from using these types of concepts. So recall that momentum is the product of mass and velocity. The direction part of the momentum is going to be equal to the direction part of the velocity, and then the magnitude part of the momentum is going to be the magnitude part of the velocity multiplied by the mass. Newton's second law is more correctly written as the change in momentum of an object is equal to the net force exerted on the object times the time that that net force is exerted. And if the net force is equal to zero, then the change in the momentum obviously is zero. Anything times zero is zero. So that means that the initial and the final momentums then are equal if the change in momentum is zero. We can extend our quote-unquote system to include the entire universe. And of course, when we do that, then we can say that the momentum is constant for the entire universe. And that's absolutely true. So the entities within the universe are exchanging momentum with one another. But if we sum up the entire universe's momentum, we get the same value today as we do tomorrow, as we do the next day, et cetera, et cetera, et cetera. So momentum is conserved for isolated systems. Our textbook likes to use prime notation for final and non-primed notation for initial. And I know this diverts from what we were using for initial and final earlier on. This is pretty traditional in all physics textbooks to use different nomenclature in different areas, and I apologize, it's confusing, but I want to stick with the nomenclature in the textbook so that you don't get confused by looking at these videos and then looking at your textbook. So this is initial momentum total for the system, and this is final momentum total for the system, final indicated by the primed sign. When you have an isolated system, then the net force is zero. So that's why we're able to say that the system's momentum doesn't change if it's an isolated system. Another quantity that is not a new quantity for us, but it gets a special name is the change in momentum. It's called impulse. So another way of saying change in momentum is impulse. And since change in momentum is the same as the net force exerted for some amount of time, then impulse is also the same thing as net force exerted for some amount of time. We have to get used to the language. Impulse is a vector quantity because it is equal to a vector quantity times a scalar quantity. So in this video, let's now expand to talk about collisions when we have two objects that collide with one another. And we're only going to consider the complexity of two objects colliding with one another. But of course, this idea can be extended to many, like, when we talk about including the entire universe, obviously there are millions upon millions upon millions of entities in our universe. And so we can extend these, collisions to include many objects. But we're just going to consider two objects in our analyses at this level. So there are two different types of collisions. There are elastic and inelastic. When two objects collide with one another, they are exerting forces on one another. So let's say that we have two objects, object 1 and object 2, that are colliding with one another. So object 2 has some initial velocity, object 1 has some initial velocity, so this is pre-collision. And then they collide, and after the collision, they have some post-collisional velocity, which again, we're going to use prime symbols for post-collisional quantities. Okay, so this is post-collision. What changed the momentum of object 1? Why did object 1's momentum change? It changed because object 2 exerted a force on object 1. So object 1's P changed due to object 2's force. Object 2's momentum changed due to object 1's force. So note that object 1 exerted a force on object 2. Simultaneously, object 2 exerted a force on object 1. So 1 exerts a force on 2, 2 exerts a force on 1. That makes up a Newton's third law pair. So that means that the magnitude of the force that 1 exerts on 2 is equal to the magnitude of the force that 2 exerts back on 1. In addition, the time that object 1 is exerting its force on object 2 is equal to the time that object 2 is exerting its force on object 1. So the change in momentum for object 1 is going to be equal to the force exerted on 1 by 2 times the time that that force was exerted. And the change in momentum for object 2 is equal to the force exerted on object 2 by object 1 times the time that that force was exerted. Notice that these are Newton's third law pair forces, so they have the same magnitude, and the times over which these forces were exerted have to be the same. In other words, 1 can't be pushing on 2 longer than 2 is being pushed by 1. These forces and times are equal to one another, so the magnitude parts of the right-hand sides of these two equations are the same, but the direction parts are different. The force exerted on 1 by 2, notice, is directed to the left. The force exerted on 2 by 1 is exerted to the right. So there's a negative sign difference between these two right-hand sides, but the magnitude parts are the same. So that means that the left-hand sides also have the same magnitude, but the signs are opposite. So then from this, via Newton's third, we can write that the change in momentum for object 1 is equal to the negative of the change in momentum for object 2. So writing this out, this is the final momentum for object 1 minus the initial momentum for object 1, that's the change in momentum for object 1, is equal to the negative of the change in momentum for object 2. I need to open up parentheses so I can be sure to distribute this negative sign correctly. So this is momentum of object 2 final post-collisional minus the momentum of object 2 pre-collisional. So if I rearrange this, what I get out of this is that P1 plus P2, this is the sum of the momentum before the collision, is equal to P1 prime plus P2 prime. That's the sum of the momentums after the collision. So this is a conservation of momentum. This is the momentum before the collision of the system is equal to the momentum of the system after the collision. Now, notice that the collision takes place over a very small space. In other words, there could be friction on this surface that's going to eat away at the velocity just after the collision. But just before the collision and just after the collision, this conservation of momentum must hold. The only forces that are considered when we have a collision, and again, this is only happening over very small space and very small time, are the internal forces exerted by each object on the other as they are actually colliding. So conservation of momentum holds for all collisions, whether they are elastic or inelastic. Every single collision must satisfy conservation of momentum such that their momentum just the nanometer before they collide, the sum of their momentum has to be equal to the sum of their momentum just the nanosecond after their collision. This conservation of momentum holds for all collisions. So conservation of momentum holds for all collisions. Sorry for the squeaky chalk. For all collisions, we will have conservation of momentum. We're going to pick up a different type of momentum as we move on to subsequent chapters, and when we do, we'll be talking about this as linear momentum specifically, because we'll be picking up a different type of momentum called angular momentum. So this is specifically linear momentum, but conservation of momentum holds for all collisions. So we can always take the momentum of the objects just before they collide and set that equal to the momentum of the objects just after they collide, and that's always going to be true. So what's the difference between elastic and inelastic? If all collisions have conservation of momentum, why do we distinguish between them? Because in elastic collisions, we also have conservation of kinetic energy. So the kinetic energy before the collision and the kinetic energy after the collision are going to be the same. So for elastic collisions, cannot write, my apologies. Kinetic energy is conserved as well. So again, momentum is conserved for all collisions. But if we have a specifically elastic collision, then kinetic energy is also conserved. Elastic collisions will be the subject of some of the problems that we consider as we look at the next video and actually work some problems from the back of this particular chapter. So we'll see you next time for that.